Hello everyone. So last time we saw that a lot of the functions that we normally work with are continuous, and we saw how to combine continuous functions to get more continuous functions. So now we're going to see a little bit of a payoff from that. So why is it helpful to have so many continuous functions? And one application of continuity, for instance, is the intermediate value theorem. So let's see what that is. So let's suppose we have a function which is continuous on a closed interval AB, so meaning it's continuous at every point of that interval, like we talked about. And let's suppose that f of a is not equal to f of b. So the value of the function at the different endpoints is different. And let's suppose that we take any number between f of a and f of b. So let n be any number between the two endpoints. And clearly, since the values at the endpoints are different, there are lots of numbers between them. So let's just pick any number we like, any number n between the endpoints. Then the intermediate value theorem tells us that there is, at some point, the function must take the value n. So at some point c in the interval ab, so somewhere between our two endpoints, the function has to cross the value n. It has to take the value n. Okay. So let's see what that looks like on a picture. So here we have a graph of a nice continuous function on AB. Remember, our function is supposed to be continuous along the whole interval AB. So here's a nice function. F of A is supposed to be different to F of B. So here, F of A is down here, F of B is up here. It's definitely, they're definitely different. And then n is supposed to be any number that we can pick, any number we like that's between f of a and f of b. So here I made a choice, I drew it up here, but the same argument would work, anywhere close to f of b, close to f of a, anywhere in the middle, as long as it's between f of a and f of b. And then I drew this line across which signifies y equals n. So this is all of these points are where the value is n. Okay. And then the conclusion of the intermediate value theorem says that at some point in the interval, so at some number c, which is between a and b, the function takes the value n. So in other words, the graph of the function at this number c, the graph of the function will cross the line y equals n. Okay, so why is this useful? Why is this interesting? Okay, before we do that, let's say why do we need these conditions? So clearly it wouldn't make any sense without f of a being different to f of b. But why do we care that f is continuous? I mean, doesn't this work for every function? And the answer is no, we really need continuity. So for instance, here is a function defined by the graph. So on the interval from 0 to 1, the value is 1. On the interval from 1 to 2, the value is 2. And at the point 1, the value is 2. So here's a function. And let's say we're trying to apply the intermediate value theorem. It's not going to work, but let's just suppose we try. So we're on the interval 0, 2. At 0, the value is 1. At 2, the value is 2. Let's pick some point in between. Let's say 1.5. Okay, in this case, there is no place where the value of the function is 1.5, right? It never crosses the line 1.5. And okay, what's going on here? Well, clearly the problem is this function is not continuous, right? This has a big jump at 1. This is not a continuous function, so we cannot apply intermediate value theorem. So if we're going to use the intermediate value theorem, we have to be really careful that the function has to be continuous. So we can only use it for continuous functions. Okay, but for continuous functions, the intermediate value theorem has a big application, which is in solving equations and finding roots to equations. So let's do an example like that. Let's try to use the IVT, it's just an abbreviation for intermediate value theorem. Let's try to use it to show that there is a root of x to the 4 plus x minus 3 in the interval from 1 to 2. So what do I mean by a root? I just mean there is a value of c that makes it 0, right? There is a solution to x to the 4 plus x minus 3 equals 0 inside 1, 2 in the open interval. So let's try to do that. So let's apply the intermediate value theorem. So we have a function, f of x is x to the 4 plus x minus 3. And it's a polynomial, so it's continuous everywhere. So whatever interval you pick, it's going to be continuous. And we're interested in particular on 1, 2. So let's try to apply the intermediate value theorem on 1, 2. Okay, so we should check the values of the endpoints. Well, f of 1 is minus 1, and f of 2 is 15. Okay, you can check, or you can trust me if you substitute, you get minus 1 and 15. Clearly they are different, so we can try to apply the intermediate value theorem. Intermediate value theorem will say that for any number between minus 1 and 15, for instance 0, we can pick 0 if we like. For any number between minus 1 and 15, there is going to be a value of c between 1 and 2 where the function takes the value we chose. So here, 0 is between minus 1 and 15. So somewhere between 1 and 2, the function has to take the value of 0. Okay, so we're applying the intermediate value theorem. There is a number c so that f of c equals 0. So this is what we wanted to show, right? We managed to use the intermediate value theorem to find a root inside the interval 1, 2. So this will be the end of the example or end of the story. But something worth knowing is that you can keep going further and further to find the root. So here, knowing the root is in 1, 2, it doesn't really help us if we want to get a good approximation or really know what the root is. So how can we keep going? So let's suppose we compute f of 1.5. So I chose 1.5 because it's in the middle of 1 and 2. We know the root is somewhere in 1, 2. Well, what side does it lie on? Is it between 1 and 1.5, or is it between 1.5 and 2? Let's say I want to find out. Well, if you compute f of 1.5, you get 3.5625, which is strictly positive. And then, okay, so on what interval should I apply the intermediate value theorem again? So I want to apply the intermediate value theorem, and I want to be able to use n equals 0. So in other words, I need the function to cross the value of 0, okay? So if I think of f of 1, that's minus 1. F of 1.5, that's 3.5625. F of 2 is 15. Okay, where could the function possibly cross the value 0? Well, that would be between minus 1 and 3.5625. Right, so if we apply the intermediate value theorem to the interval 1 to 1.5, the values at the endpoints are different. F of 1 is negative 1, F of 1.5 is 3.5625. By the intermediate value theorem, for any number between minus 1 and 3.5625, the function has to take that value. In particular, the function has to take the value 0. So the function has a root in that interval. And then we could keep going, right? We could say, okay, the root is in 1 to 1.5. Is it within 1 to 1.25, or is it within 1.25 to 1.5? Okay, I compute 1.2 f of 1.25. That's 0.6914, which is again positive. Okay, so f of 1 is strictly less than 0. F of 1.25 is strictly bigger than 0. It's a continuous function, so it's going to have to cross 0 is between the two values. So at some point, between 1 and 1.25, the value of the function has to be equal to 0. Okay, so we've gradually narrowed down our root. In the first case, we know it was between 1 and 2. Then we know that it's between 1 and 1.5. Now we know that it's between 1 and 1.25. And you could keep going and having it each time and finding the root to higher and higher accuracy. So you could find it to 1 decimal place, to 2 decimal places, and so on and so on. Okay, so and for instance, if you had a computer to write an algorithm, you could find the root to any degree of accuracy you like. Okay, so the intermediate value theorem is going to be a big application for us of continuity. So that's already one of the pairs. Okay, thanks everyone. See you next time.